So now I want to do a quick example looking at sort of scheduling in FreeRTOS. I've done a few things. I have, just to start off with, taken essentially the code from the tasks demo, and I've just sort of copied it out. I have 3 tasks now, and instead of this generic priority, I have used priority 1, because if we go into FreeRTOS config.h, which is in the include folder, as you can see here, you have this max priorities, and this says I've configured it to 10, meaning that my FreeRTOS kernel is configured to have priorities 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 being the highest, like the most important, and 1 being the least important, because the idle task falls on a 0 priority. So just quickly, I was running I was sort of recording this a second ago, and I was executing the code, and something a bit unusual happened, and then I had to figure out why. And so I just sort of want to quickly, before I start this whole this explanation, try a few things out. This might be a bit complex for some people, but I think it's just kind of good to explain like exactly what's happening. And it also shows that if something weird happens, you can just go through the source code, and it's usually, it makes sense just to find out what exactly is happening. Now, I presented this slide in the lecture just before, saying that the scheduler in FreeRTOS runs through each task priority and then executes the list, because each priority is sort of like a double list, like a 2D array, and each priority has a list, and in each priority there's a list of tasks, and they get executed sequentially, which is true. And this does exist in FreeRTOS, and I've seen this before in the source code, but then I overlooked a small thing. Well, I've just not overlooked it, I've just never really looked into that portion of the source code. And that is, I here, for instance, have 3 tasks that are all exactly the same. They will just say hello. They delay for 1, and they are created 1, 2, 3 with the same priorities. And so you would expect this to be task 1, 2, 3, and to execute in that order, 1, 2, 3. I've also configured, I should just note here, my tick to be a lot slower so that my terminal doesn't get completely spammed. Although this is, for all intensive purposes, having a 10 here makes the system not really feasible for any application, but for demonstration purposes it works quite well. And so what I did was I was expecting this 1, 2, 3 output, and then I'm building it and running it, and I'm getting 3, 2, 1. And I'm thinking, this is not correct. So I'm getting 3, 1, 2, 3, 1, 2. And so then I'm like, okay, cool. Why? But if we look, for instance, going through the task creation, so if we go into task create, we can actually go into it. We'll go to the other. I'm in the header file. So what I'll do is I'll just jump to the relevant code, which is in tasks. And so essentially xtask create it sets up the task, it allocates the stack, sets the name, blah, 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 really just straightforward stuff. And then it adds it to the list. And now this list is this one for each priority. So it essentially says add to list of the priority, and uses the priority as the index to this list. And so it adds it to this list. But then there's this line of code here. And this is what I've never come across before. And so all it's saying is that if the scheduler is not already running, so if we create a task before the scheduler is running, this code is executed. And it says if it is the highest priority task to be created, set this. So what this is this TCB stands for task control block, I believe. And so what it's saying is that in here, if this priority is the highest, make this task current, which makes sense. Like if you create a task of priority 1, 1, and then priority task of 2, you want to set the current task control block, which is sort of the task that's running, to be the highest one. Now there's a slight problem with this line, and namely here, there's this less than or equal to. So this is not just saying if the task is high priority, but if it's higher or equal to. So I don't know if this is by design or if this is an error in the source code, because the thing is that when I haven't started my scheduler, like I have it here, so these 3 tasks are entering this line of code because their scheduler is not running, it's going to evaluate and be like, hey, is the priority higher or equal to, and it will set that task to be the current task. And so what this actually does is it means that because I'm creating 3 tasks here of the same priority, when task 3 runs, it's going to execute this code and it's going to get set to the current task. And so this little bug means that, or I don't know if it's a bug, but this little equal sign means that they are created in the list, but task 3, the last of whatever you create of the same priority, of the highest priority, gets set to the current task, which doesn't really fit with the list structure that they use. So that's why I'm thinking it's not meant to be like this, but this explains my current weird behavior. Because they're executing like normal 1, 2, 3, but because this guy's already executed and blocked, he's not going to get run because he's already sitting in a block state by the time they get to the 3rd task in the list, if that makes sense. And so what I can do is I can actually remove this equals and then recompile my code, and we'll see we get the normal 1, 2, 3 because this 3rd task doesn't get put into the current the current executing task, right? But I'm just going to leave it like that because maybe it's meant to be like that, I'm not sure. But at least that explains this weird behavior I was just getting. So what I was saying is that this is true, that it does execute through this list in periodic sequence. But the thing is that there is an exception in that the last task created of the highest priority gets set to the current task. And so that means that the task 3 that would sit here has already executed and gone to a block state. So then it just goes 1, 2, then calls a scheduler, unblocks them all again, and it was the first task to sort of get evaluated, and therefore it becomes the first one to get evaluated again, if that makes sense. So the list exists, but then this one little quirk means that one task gets sort of put at the front all the time, at least for sort of this sort of application. So enough of that now. Now sort of going back to just explaining, or we'll just look at some priorities and we'll just play around a bit to sort of make it a little clearer how the priorities work. So we've created 3 tasks here, all of the same priority, and all they do is they print and they block for 1. And so this means, as we can see here, I've also modified, I think it was in port, so I think tick/n here. What I've done is that this is the port tick handler. So this is the code that runs every millisecond or every time my tick gets executed. And all I've done is I've put in a print statement because I want to be able to visually show the tick sort of separation. So this is not intuitively actually part of the code, so you won't have this, but it's just for the demonstration purposes. But so now we can see, for instance, if we change task 2 and 3's creation order, we will see, well, we should at least see an execution order change. So task 3 is always going to run first because of this little quirk, and then we get 2 and 1 because it's going sequentially down, except for the last one. We just ignore him because he's always going to be the first because of that quirk. But now let's take that back. But what we can do, for instance, is that task 2 was created. So now we have, or we'll just run this to show you that, okay, cool. Now we've put task 2 back to being created second, and so it's running after task 1. But now what happens if we increase its priority, which is what we imagine would happen now that we have like priority 1 here, essentially, and priority 2. So it's going to run priority 2 first. And so if we run this, task 2 gets executed first, and this is 2 reasons, because it's got the highest priority and it's running its list first, but because of this quirk as well, it's actually getting set to the current task at the beginning, right? So this should be, so there we can see the priority changing. What else can we do to sort of show the priorities difference? Task 2. So I had a quick brainstorm what we can do, and what I'm actually going to do is I'm going to take out this little glitch again because it's just annoying to explain everything with this one task getting out of order. Now, so taking that out now, so if we compile and run our code, we're going to get, oops, sorry, I should take this one out. Take out this, so now they're all the same priority. And we get 1, 2, 3, which is what we want. So this is really nice and easy. So now I'll just talk about like blocking. And so here we have them all blocking for 1 tick, meaning that the scheduler starts, it runs tasks 1, 2, 3. It goes through this list that we've seen here and executes 1, 2, 3. And then they all get blocked. And so what happens is if we go into vtask delay, like we saw in, or actually have the code here, you put in the time it wants to delay, and it essentially calls this yield function, port yield within API. Now, I've gone and found out where it exists, and it's in the ports file. Oops, what am I doing? Nope. Ports here, and it's yield, which can I spell it correctly? Y-E-L-D. Nope, next one. Here we go. And so if we look down through, this is the call to the scheduler, like a manual call to it. And so this is all a bit confusing and whatever, but there's a few things that we need to sort of, we can read the code because of the names of the functions to get an idea of what's happening. So what they're doing here is they're sort of getting the current task, right? And then they're saying, okay, get the thread of that task, like get us the actual structure. And then it says, okay, if the task that we want to stop and the task we want to resume are different, then start the new task and stop the old task, right? So it's pretty simple. It's saying, okay, cool, get an old one and get the new one, and if they're not the same, then resume it. And all it's doing is to get the new task, it's running this function here, vtask context switch, which we can maybe find here. And what this does is it uses, if I find it, select highest priority task. So all it's doing before it's checking the new task and the old task, it's firstly setting the new task to the next highest priority task. And so if we go into this one, it's going to look at this ready task list with the top priority and just return return the next one. So what this is going to do is it's just going to return the highest priority, and then it's going to get the next entry and put it into the current task control block from the ready task list. So here it's finding the highest priority, which is then used as an index. So it's essentially finding, finding which row of this figure needs to execute, and then it's then it's setting the current task control block to the next one in that list. Because of they have these list structures where you can sort of iterate, you can just call it and get an iterator for it. So that's what's happening here. So if we go back to our where is it? Yes, here. Nope. Port yield. This is setting the current task, like the current highest priority task, which is then gotten from here as the task to resume, so the next task. And then it does this to suspend, to resume, are they the same, and if not, it just switches them, right? And so in this case, the actual context swap doesn't have any of this save the status register, set all the registers and then whatever, because this is on top of POSIX. So all of that stuff is done using the pthread library. So it is happening, but it's just abstracted away because of this implementation. Oops, so get rid of that. So I want to show that that's what's happening when we block, is that essentially we cause it to suspend, and then we call the scheduler, right? And so this means that we can have multiple tasks executing within one tick. So let's do a quick example using these, that what happens when we move around these delays, and sort of it'll just make sense what's happening. So a really basic example would be, like at the moment we have task 1, 2, 3 executing sequentially because they're getting created in that order, 1, 2, 3. We've gotten rid of this glitch in the source code, and now they all block, and then they block all for one tick and they resume. So if we, for instance, add this delay here to be like 2, we'll see that this task 1 will run, it will sleep for one tick, meaning it will execute the next tick. Task 2 will run, it will sleep for one tick, which means it executes the next tick, right? So this number here means how many ticks later in reference to the current tick. So 1 tick later meaning the next tick. And so this one here will be 2 ticks later, meaning the next tick it will still be blocked, and then we'll resume execution the following tick. So if we make and run this, we'll see that we have 1, 2, 3, which is what we expect. They're all running the first time. They're all then getting blocked. And then task 3 is not executing because it was blocked. But we can see here that is now being resolved earlier than the others because it's at the beginning of this sort of check if it's to be moved from block to ready list. And so this is getting done first. And so it's getting put higher on the ready list and then getting run. But it's essentially sleeping for 1 tick, which is what we want. And so we can do, for instance, things like we can move this, or we'll move this delay here, and we'll put it up here. So what will happen here is that the first tick's going to execute. It's going to run 1 and 3, which is what we expect. They get created and run. Task 1 then blocks for a tick, and task 3 blocks for 2 ticks. And in the second tick, we get 1 and 2. Now, why is this? Because 1 is executing every tick, essentially. It's sleeping until the next tick, so it's just running every tick. But task 2 executes the first time, hits the delay, enters the block state until the next tick. So it's only going to execute for the first time on the second tick. But after that, it's just going to keep executing each tick. But it's sort of in the inverse way that it's going to block and then print with a 1 tick delay at the beginning, as we can see here. So this should maybe make sense that when we go to think about sort of like how things are blocked and woken up, usually the actual order of things doesn't matter, because if you're using the order of task creation to ensure the order of your execution of your program, then this is a badly written program. And so that is why the bugs that here, this shouldn't actually really impact your task or your program's execution, because if you require a certain order of your task execution, then you need to use synchronization methods, which we'll get to in the lecture very shortly. But the idea of this sort of like blocking and then resuming is what I want to try to get here, is that the scheduler will use calls to certain sort of delays or synchronization methods to put tasks into the block state, which are then reevaluated every tick. And then the tick decides whether the task should be moved to the ready state so that it can be then scheduled. And so the scheduler doesn't actually decide, okay, we're going to run 3, 1, 2 here. It's going to decide, okay, we're going to run 3, and 3 will run and then hit this block delay thing, and then delay will actually invoke the context switch manually here, which is actually what we saw in this figure, in that the scheduler is called again after the applications or the task code is executed. So I think hopefully this little example made this figure and as well as this, wherever the other one is, this one a little clearer.